Learning objectives. In this chapter, the user will learn the following in detail: aggregate method, counting method, potential method, and dynamic table. Accounting method. In accounting method of amortized analysis, assign differing charges to different operations, with some operations charged more or less than they actually cost. Amount we charge an operation, its amortized cost. When an operation's amortized cost exceeds its actual cost, then assign the difference to specific object in the data structure as credit. Credit can help pay for later operations whose amortized cost is less than their actual cost. The amortized cost of an operation as being split between its actual cost and credit that is either deposited or used up. Different operations may have different amortized costs. This method differs from aggregate analysis, in which all operations have the same amortized cost. Choose the amortized cost of operations carefully. If we want to show that in the worst case, the average cost per operation is small by analyzing with amortized costs, we must ensure that the total amortized cost of a sequence of operations provides an upper bound on the total actual cost of the sequence. Moreover, as in aggregate analysis, the relationship must hold for all sequences of operations. If we denote the actual cost of the ith operation by C power I and the amortized cost of the ith operation by Ci cap, require summation I equals 1 to n Ci cap greater than or equals summation I equals 1 to n Ci for all sequences of n operations. The total credit stored in the data structure is the difference between the total amortized cost and the total actual cost, or summation I equals 1 to n Ci cap minus summation I equals 1 to n Ci. The total credit associated with the data structure must be non-negative at all times. If allow the total credit to become negative, the result of undercharging early operations with the promise of repaying the account later on, then the total amortized costs incurred at that time would be below the total actual cost incurred. For the sequence of operations up to that time, the total amortized cost would not be an upper bound on the total actual cost. Thus, the total credit in the data structure never becomes negative. Stack operations. To illustrate the accounting method of amortized analysis, let us return to the stack example. Recall that the actual costs of the operations were push 1, pop 1, multipop, min of k, s, where k is the argument supplied to multipop and s is the stack size when it is called. Let us assign the following amortized cost: push 2, pop 0, multipop 0. Note that the amortized cost of multipop is a constant of 0, whereas the actual cost is variable. Here all three amortized costs are constant. In general, the amortized costs of the operations under consideration may differ from each other, and they may even differ asymptotically. Show that we can pay for any sequence of stack operations by charging the amortized cost. Suppose we use a dollar bill to represent each unit of cost. We start with an empty stack. When we push a plate on the stack, we use $1 to pay the actual cost of the push and are left with a credit of $1 out of the $2 charged, which we leave on top of the plate. At any point in time, every plate on the stack has $1 of credit on it. The dollar stored on the plate serves as prepayment for the cost of popping it from the stack. When we execute a pop operation, charge the operation nothing and pay its actual cost using the credit stored on the stack. To pop a plate, take the dollar of credit of the plate and use it to pay the actual cost of the operation. Thus, by charging the push operation a little bit more, charge the pop operation nothing. Moreover, also charge multi-pop operations, nothing. To pop the first plate, we take the dollar of credit of the plate and use it to pay the actual cost of a pop operation. To pop a second plate, again have a dollar of credit on the plate to pay for the pop operation and so on. Thus, always charged enough upfront to pay for multi-pop operations. In other words, since each plate on the stack has $1 of credit on it, and the stack always has a non-negative number of plates, ensured that the amount of credit is always non-negative. For any sequence of n push, pop and multi-pop operations, the total amortized cost is an upper bound on the total actual cost. Since the total amortized cost is big O of n is the total actual cost. Incrementing a binary counter. As another illustration of the accounting method, we analyze the increment operation on a binary counter that starts at 0. As we observed earlier, the running method of this operation is proportional to the number of bits flipped, which we shall use as our cost for this example. Let us use a dollar bill to represent each unit of cost, the flipping of a bit in this example. For the amortized analysis, let us charge an amortized cost of $2 to set a bit up to 1. When a bit is set, we use $1 out of the $2 charged to pay for the actual setting of the bit and place the other dollar on the bit as credit to be used later when we flip the bit back to 0. At any point in time, every one in the counter has a dollar of credit on it and charge nothing to reset a bit to 0. Just pay for the reset with the dollar bill on the bit. Now we can determine the amortized cost of increment. The cost of resetting the bits within the while loop is paid for by the dollars on the bits that are reset. The increment procedure sets at most 1 bit in line 6, and therefore the amortized cost of an increment operation is at most $2. The number of ones in the counter never becomes negative and the amount of credit stays non-negative at all times. Thus, for n increment operations, the total amortized cost is big O of n, which bounds the total actual cost. Aggregate method. Amortized analysis. It guarantees the average performance of each operation in the worst case. 3 most common techniques used in amortized analysis. Aggregate analysis. Total cost of n operations by n. This method used to determine an upper bound T of n on the total cost of a sequence of n operations. The average cost per operation is then T of n equals n, so that all operations have the same amortized cost. Accounting method used to determine an amortized cost of each operation. When there is more than one type of operation, each type of operation may have a different amortized cost. Overcharges some operations early in the sequence, storing the overcharge as prepaid credit on specific objects in the data structure. Later in the sequence, the credit pays for operations that are charged less than the actually cost. Potential method, same as accounting method. Determine the amortized cost of each operation and may overcharge operations early on to compensate for undercharges later. The potential method maintains the credit as the potential energy of the data structure. Here, we are using 2 examples for examining these 3 methods. Stack with the additional operation multi-pop pops several objects at once. Binary counter that counts up from 0 by means of the single operation increment. In the worst case, the average cost or amortized cost per operation is therefore T of n equals n. Note that this amortized cost applies to each operation, even when there are several types of operations in the sequence. Bear in mind The charges assigned during an amortized analysis are for analysis purpose only. They need not and should not appear in the code. For example, if we assign a credit to an object X when using an accounting method, then no need to assign an appropriate amount to some attribute such as X.credit in the code. Aggregate analysis. In the worst case, the average cost or amortized cost per operation is T of n by n. This amortized cost applies to each operation even when there are several types of operations in the sequence. In aggregate analysis, a sequence of n operations takes worst case time T of n in total, the average cost as the amortized cost of each operation. Aggregate analysis example: stack operations. Analyze stacks that have been augmented with a new operation. Two basic stack operations which takes big O of 1 time. Push of S, X pushes object X onto the stack S. Pop of S pops the top of stack S and returns the popped object. Calling pop on an empty stack generates an error. Since each of these operations runs in big O of 1 time, let us consider the cost of each to be 1. The total cost of a sequence of n push and pop operations is therefore n, and the actual running time for n operations is therefore theta of n. Add the stack operation multipop of S, K, which removes k top objects of stack S, popping the entire stack if the stack contains fewer than k objects. Of course, we assume that k is positive, otherwise the multipop operation leaves the stack unchanged. In the following pseudocode, the operation stack empty returns true if there are no objects currently on the stack, and false otherwise. The action of multipop on a stack S shown initially in the below figure. The top 4 objects are popped by multipop of S, 4, whose result is shown in this figure. The next operation is multipop of S, 7, which empties the stack. Example of multipop shown in this figure. What is the running time of multipop of S, K on a stack of S objects? The actual running time is linear in the number of pop operations actually executed, and thus we can analyze multipop in terms of the abstract costs of 1 each for push and pop. The number of iterations of the while loop is the number min of S, K of objects popped of the stack. Each iteration of the loop makes one call to pop in line 2. Thus, the total cost of multipop is min of S, K, and the actual running time is a linear function of this cost. Let us analyze a sequence of n push, pop, and multipop operations on an initially empty stack. The worst case cost of a multipop operation in the sequence is big O of n, since the stack size is at most n. The worst case time of any stack operation is therefore big O of n, and hence a sequence of n operations costs big O of n square. Since we may have big O of n multipop operations costing big O of n each. Although this analysis is correct, the big O of n square result, which we obtained by considering the worst case cost of each operation individually, is not tight. Using aggregate analysis, we can obtain a better upper bound that considers the entire sequence of n operations. In fact, although a single multipop operation can be expensive, any sequence of n push, pop, and multipop operations on an initially empty stack can cost at most big O of n. Why? Pop each object from the stack at most once for each time we have pushed it onto the stack. Therefore, the number of items that pop can be called on a non-empty stack, including calls within multi-pop, is at most the number of push operations, which is at most n. For any value of n, any sequence of n push, pop and multi-pop operations takes a total of big O of n time. The average cost of an operation is big O of n by n equals big O of 1. In aggregate analysis, assign the amortized cost of each operation to be the average cost. In this example, all three stack operations have an amortized cost of big O of 1. Emphasize again that although we have just shown that the average cost and hence the running time of a stack operation is big O of 1, did not use probabilistic reasoning. A worst case bound of big O of n on a sequence of n operations. Dividing this total cost by n yielded the average cost per operation or the amortized cost. Incrementing a binary counter. This is another example of aggregate analysis. Consider the problem of implementing a k-bit binary counter that counts upward from 0. Use an array A of 0 to k-1 of bits, where a.length equals k as the counter. A binary number x that is stored in the counter has its lowest order bit in A of 0 and its highest order bit in A of k-1. So that x equals summation of I equals 0 to k-1, A of I and 2 power I. Initially, x equals 0 and thus A of I equals 0 for I equals 0 up to k-1. To add 1 modulo 2 power k to the value in the counter, we use the procedure which is shown here. At the start of each iteration of the while loop in lines 2 to 4, to add a1 into position I. If A of I equals 1, then adding 1 flips the bit to 0 in position I and yields a carry of 1 to be added into position I plus 1 on the next iteration of the loop. Otherwise, the loop ends and then, if I less than k, A of I equals 0. So that line 6 adds a 1 into position I, flipping the 0 to a 1. The cost of each increment operation is linear in the number of bits flipped. As with the stack example, a cursory analysis yields a bound that is correct but not tight. A single execution of increment takes time big theta of k in the worst case, in which array A contains all ones. Thus a sequence of n increment operations and an initially 0 counter takes time big O of nk in the worst case. Tighten analysis to yield a worst case cost of big O of n for a sequence of n increment operations by observing that not all bits flip each time increment is called. As the below figure shows, A of 0 does flip each time increment is called. The next bit up, A of 1, flips only every other time. A sequence of n increment operations on an initially 0 counter causes A of 1 to flip flow of n by 2 times. Similarly, bit 2 flips only every 4th time or floor of n by 4 times in a sequence of n increment operations. In general, for I equals 0 up to k-1, bit A of I flips floor of n by 2 power I times in a sequence of n increment operations on an initially 0 counter. For I greater than or equal to k, bit A of I does not exist and so it cannot flip. Following figure shows an 8-bit binary counter as its value goes from 0 to 16 by a sequence of 16 increment operations. Bits that flip to achieve the next value are shaded. The running cost for flipping bits is shown at the right. Notice that the total cost is always less than twice the total number of increment operations. The total number of flips in the sequence is thus as shown in the screen. Dynamic table. Do not always know in advance how many objects some applications will store in a table. Allocate space for a table only to find out later that is not enough. Then reallocate the table with a larger size and copy all objects stored in the original table over into the new larger table. Similarly, if many objects have been deleted from the table, it may be worthwhile to reallocate the table with a smaller size. In this section, we study this problem of dynamically expanding and contracting a table. Using amortized analysis, show that the amortized cost of insertion and deletion is only big O of 1, even though the actual cost of an operation is large, when it triggers an expansion or a contraction. Moreover, how to guarantee that the unused space in a dynamic table never exceeds a constant fraction of the total space. Assume that the dynamic table supports the operations table insert and table delete. Table insert inserts into the table an item that occupies a single slot, that is, a space for one item. Likewise, table delete removes an item from the table, thereby freeing a slot. The details of the data structuring method used to organize the table are unimportant. Use a stack, a heap, a hash table, or an array or collection of arrays to implement object storage. To use a concept introduced in our analysis of hashing, define the load factor alpha of T of a non-empty table T to be the number of items stored in the table divided by the size, number of slots of the table. Assign an empty table 1 with no items, size 0, and we define its load factor to be 1. If the load factor of a dynamic table is bounded below by a constant, the unused space in the table is never more than a constant fraction of the total amount of space. Start by analyzing a dynamic table in which we only insert items, then consider the more general case in which we both insert and delete items. Table expansion. Let us assume that storage for a table is allocated as an array of slots. A table fills up when all slots have been used or equivalently, when its load factor is 1. In some software environments, upon attempting to insert an item into a full table, the only alternative is to abort with an error. Assume, however, that our software environment, like many modern ones, provides a memory management system that can allocate and free blocks of storage on request. Thus, upon inserting an item into a full table, expand the table by allocating a new table with more slots than the old table had. Because always need the table to reside in contiguous memory, we must allocate a new array for the larger table and then copy items from the old table into the new table. A common heuristic allocates a new table with twice as many slots as the old one. If the only table operations are insertions, then the load factor of the table is always at least 1 by 2, and thus the amount of wasted space never exceeds half the total space in the table. In the following pseudocode, assume that T is an object representing the table. The attribute T.table containing a pointer to the block of storage representing the table. T.num contains the number of items in the table, and T.size gives the total number of slots in the table. Initially, the table is empty. T.num equals T.size equals 0. The pseudocode of table insert is shown in this figure. We have two insertion procedures. Here, the table insert procedure itself and the elementary insertion into a table in lines 6 and 10. We can analyze the running time of table insert in terms of the number of elementary insertions by assigning a cost of 1 to each elementary insertion. We assume that the actual running time of table insert is linear in the time to insert individual items, so that the overhead for allocating an initial table in line 2 is constant, and the overhead for allocating and freeing storage in lines 5 and 7 is dominated by the cost of transferring items in line 6. We call the event in which lines 5 to 9 are executed an expansion. Let us analyze a sequence of n table insert operations on an initially empty table. What is the cost Ci of the ith operation? If the current table has room for the new item, or if this is the first operation, then Ci equals 1, since we need only perform the one elementary insertion in line 10. If the current table is full, however, and an expansion occurs, then Ci equals I. The cost is 1 for the elementary insertion in line 10 plus I minus 1 for the items that we must copy from the old table to the new table in line 6. If we perform n operations, the worst case cost of an operation is big O of n, which leads to an upper bound of big O of n square on the total running time for n operations. This bound is not tight because we rarely expand the table in the course of n table insert operations. Specifically, the ith operation causes an expansion only when I minus 1 is an exact power of 2. The amortized cost of an operation is, in fact, big O of 1, as we can show using aggregate analysis. The cost of the ith operation is Ci equals I if I minus 1 is an exact power of 2. Ci equals 1 otherwise. The total cost of n table insert operations is shown in this figure. Because at most n operations cost 1 and the costs of the remaining operations form a geometric series. Since the total cost of n table insert operations is bounded by 3n, the amortized cost of a single operation is at most 3. By using the accounting method, gain some feeling for why the amortized cost of a table insert operation should be 3. Intuitively, each item pays for 3 elementary insertions, inserting itself into the current table, moving itself when the table expands, and moving another item that has already been moved once when the table expands. For example, suppose that the size of the table is m immediately after an expansion. Then the table holds m by 2 items and it contains no credit. Charge $3 for each insertion. The elementary insertion that occurs immediately costs $1. Place another $1 as credit on the item inserted. Place the third $1 as credit on one of the m by 2 items already in the table. The table will not fill again until we have inserted another m by 2 minus 1 items, and thus by the time the table constrains m items and is full. Place a $1 on each item to pay to reinsert it during the expansion. Use the potential method to analyze a sequence of n table insert operations to design a table delete operation that has an big O of 1 amortized cost as well. Start by defining a potential function phi that is 0 immediately after an expansion, but builds to the table size by the time the table is full, so that pay for the next expansion by the potential. The function phi of t equals 2 and t.num minus t.size is one possibility. Immediately after an expansion, t.num equals t.size by 2 and thus phi of t equals 0. Immediately before an expansion, t.num equals t.size and thus phi of t equals t.num. The initial value of the potential is 0, and since the table is always at least half full, t.num greater than or equal to t.size by 2 which implies that phi of t is always non-negative. Thus, the sum of the amortized costs of n table insert operations gives an upper bound on the sum of the actual costs. To analyze the amortized cost of the ith table insert operation, let num I denote the number of items stored in the table after the ith operation. Size I denote the total size of the table after the ith operation, and phi I denote the potential after the ith operation. Initially, num 0 equals 0, size not equals 0, and phi not equals 0. If the ith table insert operation does not trigger an expansion, then we have size I equals size I minus 1, and the amortized cost of the operation is shown here. If the ith operation does trigger an expansion, then we have size I equals 2 into size I minus 1, and size I minus 1 equals num I minus 1 is equals num I minus 1, which implies that size I equals 2 into num I minus 1. Thus, the amortized cost of the operation is shown here. This figure plots the values of num I, size I, and I against phi I. Notice how the potential builds to pay for expanding the table. It shows the effect of a sequence of n table insert operations on the number num I of items in the table, the number size I of slots in the table, and the potential phi I equals 2 into num I minus size I, each being measured after the ith operation. In this figure, thin line shows num I, dashed line shows size I, and thick line shows phi I. Notice that immediately before an expansion, the potential has built up to the number of items in the table and therefore can pay for moving all the items to the new table. Afterwards, the potential drops to 0, but it is immediately increased by 2 upon inserting the item that caused the expansion. Table expansion and contraction. To implement a table delete operation, it is simple enough to remove the specified item from the table. In order to limit the amount of wasted space, however, we might wish to contract the table when the load factor becomes too small. Table contraction is analogous to table expansion when the number of items in the table drops too low. Allocate a new, smaller table and then copy the items from the old table into the new one. Then free the storage for the old table by returning it to the memory management system. Preserve two properties. The load factor of the dynamic table is bounded below by a positive constant. The amortized cost of a table operation is bounded above by a constant. Measure the cost in terms of elementary insertions and deletions. Double the table size upon inserting an item into a full table and half the size when deleting an item would cause the table to become less than half full. This strategy would guarantee that the load factor of the table never drops below 1/2, but unfortunately can cause the amortized cost of an operation to be quite large. Consider the following scenario. Perform n operations on a table T where n is an exact power of 2. The first n/2 operations are insertions, which by previous analysis cost a total of big theta of n. At the end of this sequence of insertions, t.num equals t.size is equals n/2. For the second n/2 operations, perform the following sequence. Insert, delete, delete, insert, insert, delete, delete, and so on. The first insertion causes the table to expand to size n. The two following deletions cause the table to contract back to size n/2. Two further insertions cause another expansion and so forth. The cost of each expansion and contraction is big theta of n, and there are big theta of n of them. The total cost of the n operations is big theta of n square, making the amortized cost of an operation big theta of n. The downside of this strategy is obvious. After expanding the table, do not delete enough items to pay for a contraction. Likewise, after contracting the table, do not insert enough items to pay for an expansion. Improve upon this strategy by allowing the load factor of the table to drop below 1 by 2. Specifically, continue to double the table size upon inserting an item into your full table, but half the table size when deleting an item causes the table to become less than 1 by 4 full rather than 1 by 2 full as before. The load factor of the table is therefore bounded below by the constant 1 by 4. Consider a load factor of 1 by 2 to be ideal, and the table's potential would then be 0. As the load factor deviates from 1 by 2, the potential increases so that by the time expand or contract the table has garnered sufficient potential to pay for copying all the items into the newly allocated table. Thus, need a potential function that has grown to t.num by the time that the load factor has either increased to 1 or decreased to 1 by 4. After either expanding or contracting the table, the load factor goes back to 1 by 2 and the table's potential reduces back to 0. Omit the code for table delete since it is analogous to table insert. For our analysis, assume that whenever the number of items in the table drops to 0, free the storage for the table. That is, if t.num equals 0, then t.size equals 0. Use the potential method to analyze the cost of a sequence of n table insert, table delete operations. Start by defining a potential function phi that is 0 immediately after an expansion or contraction and builds as the load factor increases to 1 or decreases to 1 by 4. Let us denote the load factor of a non-empty table T by alpha of T equals t.num by t.size. Since for an empty table, t.num equals t.size is equals 0 and alpha of t equals 1, always have t.num equals alpha of t.size, whether the table is empty or not. Use potential function which is shown here. Observe that the potential of an empty table is 0 and that the potential is never negative. Thus, the total amortized cost of a sequence of operations with respect to phi provides an upper bound on the actual cost of the sequence. Before proceeding with a precise analysis, pause to observe some properties of the potential function as illustrated in this figure. The effect of a sequence of n table insert and table delete operations on the number num I of the items in the table, the number size I of slots in the table, and the potential phi I equals 2 into num I minus size I if alpha I greater than or equal to 1 by 2, size I by 2 minus num I if alpha I less than 1 by 2. Each measured after the ith operation. Thin line shows num I, dashed line shows size I, and thick line shows phi I. Notice that immediately before an expansion, the potential has built up to the number of items in the table, and therefore it can pay for moving all the items to the new table. Likewise, immediately before a contraction, the potential has built up to the number of items table. When the load factor is 1 by 2, the potential is 0. When the load factor is 1, t.size equals t.num, which implies phi of t equals t.num, and thus potential can pay for an expansion if an item is inserted. When the load factor is 1 by 4, have t.size equals 4 into t dot num, which implies phi of t equals t dot num, and thus the potential can pay for a contraction if an item is deleted. To analyze a sequence of n table insert and n table delete operations, let Ci denote the actual cost of the ith operation. Ci cap denote its amortized cost with respect to phi. Num I denote the number of items stored in the table after the ith operation. Size I denote the total size of the table after the ith operation. Alpha I denote the load factor of the table after the ith operation. And phi I denote the potential after the ith operation. Initially, num not equals 0, size not equals 0, alpha not equals 1, and phi not equals 0. Start with the case in which the ith operation is table insert. The analysis is identical to that for table expansion. Whether the table expands or not, the amortized cost Ci cap of the operation is at most 3. If alpha I minus 1 less than 1 by 2, the table cannot expand as a result of the operation, since the table expands only when alpha I minus 1 equals 1. If alpha I less than 1 by 2 as well, then the amortized cost of the ith operation is shown here. If alpha I minus 1 less than 1 by 2, but alpha I greater than or equal to 1 by 2, then the result is shown here. Thus, the amortized cost of a table insert operation is at most 3. Turn to the case in which the ith operation is table delete. In this case, num I equals num I minus 1 minus 1. If alpha I minus 1 less than 1 by 2, then consider whether the operation causes the table to contract. If it does not, then size I equals size I minus 1, and the amortized cost of the operation is shown here. If alpha I minus 1 less than 1 by 2, and the ith operation does trigger a contraction, then the actual cost of the operation is Ci equals num I plus 1, since we delete one item and move num I items. Size I by 2 equals size I minus 1 by 4 is equals num I minus 1 equals num I plus 1. And the amortized cost of the operation is shown here. When the ith operation is a table delete and alpha I minus 1 greater than or equals 1 by 2, the amortized cost is also bounded above by a constant. The amortized cost of each operation is bounded above by a constant. The actual time for any sequence of n operations on a dynamic table is big O of n. Potential method. The potential method of amortized analysis represents the prepaid work as potential energy or potential, which can be released to pay for future operations. Associate the potential with the data structure as a whole rather than with specific objects within the data structure. The potential method will perform n operations, starting with an initial data structure D0. For each I equals 1 up to n, let Ci be the actual cost of the ith operation and Di be the data structure that results after applying the ith operation to data structure Di minus 1. A potential function phi maps each data structure Di to a real number phi of Di, which is the potential associated with data structure Di. The amortized cost Ci cap of the ith operation with respect to potential function phi is defined by this figure. The amortized cost of each operation is therefore its actual cost plus the change in potential due to the operation. From the above figure equation, the total amortized cost of the n operations is shown in this figure. If define a potential function phi so that phi of dn equals phi of d0, then the total amortized cost summation I equals 1 to n Ci cap gives an upper bound on the total actual cost, summation of I equals 1 to n Ci. In practice, do not always know how many operations might be performed. Therefore, if we require that phi of di greater than or equals phi of d naught for all I, then we guarantee, as in the accounting method, that we pay in advance. Usually, just define phi of d naught to be 0 and then show that phi of di greater than or equal to 0 for all I. Intuitively, if the potential difference phi of di minus phi of di minus 1 of the ith operation is positive, then the amortized cost Ci cap represents an overcharge to the ith operation and the potential of the data structure increases. If the potential difference is negative, then the amortized cost represents an undercharge to the ith operation and the decrease in the potential pays for the actual cost of the operation. The amortized cost defined by the above two equations depends on the choice of the potential function phi. Different potential functions may yield different amortized costs yet still be upper bounds on the actual costs. We often find trade-offs that we can make in choosing a potential function. The best potential function is to use depends on the desired time bounds. Stack operations. Illustrate the potential method by the example of stack operations push, pop, and multi-pop. Define the potential function phi on a stack to be the number of objects in the stack. For the empty stack d naught with which we start, we have phi of d naught equals 0. Since the number of objects in the stack is never negative, the stack di that results after the ith operation has non-negative potential and thus phi of di greater than or equals 0 is equals phi of d naught. The total amortized cost of n operations with respect to phi therefore represents an upper bound on the actual cost. Let us now compute the amortized costs of the various stack operations. If the ith operation on the stack containing s objects in a push operation, then the potential difference is shown in this figure. The amortized cost of this push operation is shown here. Suppose that the ith operation on the stack is multipop of s, k, which causes k dash equals min of k, s objects to be popped off the stack. The actual cost of the operation is k naught and the potential difference is phi of di minus phi of di minus 1 equals minus k dash. Thus, the amortized cost of the multipop operation is shown here. Similarly, the amortized cost of an ordinary pop operation is 0. The amortized cost of each of the three operations is big O of 1 and thus the total amortized cost of a sequence of n operations is big O of n. Since we have already argued that phi of di greater than or equal to phi of d naught, the total amortized cost of n operations is an upper bound on the total actual cost. The worst case cost of n operations is therefore big O of n. Incrementing a binary counter. Another example of the potential method, look at incrementing a binary counter. This time, define the potential of the counter after the ith increment operation to be bi, the number of ones in the counter after the ith operation. Let us compute the amortized cost of an increment operation. Suppose that the ith increment operation resets ti bits. The actual cost of the operation is therefore at most ti plus 1. Since in addition to resetting ti bits, it sets at most 1 bit to 1. If bi equals 0, then the ith operation resets all k bits and so bi minus 1 equals ti is equals k. If bi greater than 0, then bi equals bi minus 1 minus ti plus 1. In either case, bi less than or equal to bi minus 1 minus ti plus 1 and the potential difference is phi of di minus phi of di minus 1 less than or equal to bi minus 1 minus ti plus 1 minus bi minus 1 is equals 1 minus ti. The amortized cost is therefore Ci cap equals Ci plus phi of di minus phi of di minus 1 less than or equals ti plus 1 minus ti equals 2. If the counter starts at 0, then phi of d naught equals 0. Since phi of di greater than or equals 0 for all I, the total amortized cost of a sequence of n increment operations is an upper bound on the total actual cost. And so, the worst case cost of n increment operations is big O of n. The potential method gives an easy way to analyze the counter even when it does not start at 0. The counter starts with b naught once, and after n increment operations it has bn once, where 0 less than or equal to b naught, bn less than or equal to k. K is the number of bits in the counter. Rewrite the total cost of amortized equation is shown in this figure. Since phi of d naught equals b naught and phi of dn equals bn, the total actual cost of n increment operations is summation of I equals 1 to n Ci less than or equal to summation of I equal to 1 to n 2 minus bn plus b naught is equals 2n minus bn plus b naught. Since b naught less than or equal to k, as long as k equals big O of n, the total actual cost is big O of n. If we execute at least n equals big omega of k increment operations, the total actual cost is big O of n. Conclusion. In this chapter, we have covered the following in detail: aggregate method, accounting method, potential method, and dynamic table.